So, what is the characteristic of this circuit now? The voltage here, effective voltage here is equal to this side it is sitting at V sat plus minus, and this is sitting at V reference. So, the voltage here will be equal to, let me call it V 0 instead of saying sat, it may be plus or minus. So, then the V is equal to V 0 minus V reference divided by R 1 plus R 2 into R 1 V 0 minus. This voltage minus the drop is nothing but current multiplied by resistance. So, the current is this and multiplied by resistance R 1, which is equal to what? V 0 into R 2 by R 1 plus R 2 minus V reference by R 1 plus R 2 into R 1. Right? Because V 0 minus the minus V 0 R 1 by R 2, subtract to get R 2 by R 1 plus R 2. And so, now this voltage is sitting at V. Now, you look at the same circuit here, the plus is sitting at V reference. Now, my V reference is no more, this to be same V reference, but some value V given by this. But now, depend upon what is V 0. V 0 can be either plus sat or minus sat, and there must be compatibility between the performance of this device with respect to what you get at the output. Okay. So, let us see what the characteristic will be. If this fellow is sitting at, let's assume it is sitting at V sat plus. If it is sitting at V sat plus, this V 0 will be plus V sat, okay, and this minus this. So, whatever is this voltage must be compatible with the input here. So, the input must be lower than this voltage. For this to, we want it to be plus V sat. So, this voltage must be lower than this for this to be V sat, right. And that value will be equal to V sat, let me call this V A or V B. As long as this is sitting at plus V sat, there will be some voltage here corresponding with V 0 substituted plus V sat, and as long as this voltage is then less than this voltage, then the output will be sitting at V sat, they are compatible. So, that will be the characteristic. So, it continues like this, but when you are coming downwards, then the characteristic will move like this. I am drawing something wrong. Let me just write down this V A Let me call these some voltages VB and VA.
Excuse me, sir. Sir, here you will have the plus sign here. That's why here you at the bottom you will have the plus sign there. That will be consistent with that one. So V0 minus Vref. So you have on the last line that will be a plus sign. The last line, sir. The calculation is correct. Just the algebra on the last line.
There is nothing wrong in this, right?
Sir, the last line, the algebra, the minus will be plus sign.
Oh.
That's why you went around there.
That is where I am getting good.
Yes.
So, yeah, this way plus sign. That's where things are going wrong. Okay. So, let me call this when this is same for both first term. The second term will be plus or minus depending upon V0 being a plus Vsat or minus Vsat. So, I am calling these two voltages with Vsat being positive, Vsat being negative as equal to Va and Vb. The characteristic comes out to be, you can just argue it out, V in V0 will look like this. This point is Vb, this point is Va. You can argue it out. As long as Vin is less than Vb, Vin is less than Vb, this fellow will sit at VCC, V plus VCC, Vsat plus Vsat. Both input and output are now compatible. And then when Vb voltage goes beyond Vb, then it will go negative. But while coming back, this fellow is sitting at minus. So, the second equation will be valid with V0 equal to minus Vsat and the transition occurs at Va. So, you can see that the characteristic of this V0 Vn will be like this. So, it goes like this, like this, like this, like this, but while coming back it goes like this. And such characteristic we call it as a hysteresis. So, the Schmidt trigger has the hysteresis. I can decrease this width of the hysteresis by adjusting my V reference for a given value magnitude of Vsat. I can decrease this by proper choice of my V reference, but you will still always have some amount of hysteresis in this. What is the implication of this? The implication of this if you put a sine wave, this will not be an ideal zero crossing detector, right? It will start changing a slightly larger value for the positive side and a different value for the negative side. Right? Transitions will occur at different points in the positive side of the half cycle and the negative side of the half cycle. So, this will not be realistically speaking a square wave, but there will be some difference in this, and the difference will depend upon what is the width of this, which of course can be controlled by using the proper V reference to some extent.
Excuse me, sir. So this is voltage versus voltage we have drawn. On that plot we have a hysteresis. So this loop does not tell us that there will be any power loss anywhere, because this is voltage versus voltage. So there is no question of power hysteretic loss here.
No, no.
There is no question. And sir, this is the second time in this course you have put the feedback on that positive terminal, sir.
Hmm.
So that's not a God-given rule that we can't do it.
That's what I'm saying. Normally, for stability purposes, you do not want a output to be connected to positive terminal of the input. But here I am intentionally doing it because I want to decrease the window of this operation amplifier input voltage to make into as small as possible. So, this positive feedback is actually making the curve vertical. In the previous case also, in the negative resistance also, we provided feedback to the plus terminal, right? And only when the feedback to the plus terminal is more than the feedback to the negative terminal, you get a negative resistance. And the negative resistance is a manifestation of the positive feedback. And it has a potential to oscillate, right? So, that is what we are using actually in oscillator, that potential. So, this is the characteristic of the Schmidt trigger, which is, do not think it is hysteresis is a pain in the neck. Hysteresis is a very useful information. For example, this is used, for example, you are pumping water into the water tank on the top. You have motor. Okay. Now, you want the water tank filling to stop when the height of the water goes beyond some value. And when it goes below some value, you want the motor to below the motor to stop when it goes beyond some value. You start the motor when the water level goes below some value. This is my value correspond to shutting of the motor, and this value corresponding to turning on the motor, right? And you want it to be two different values because you want some height of the water in the tank. If this is not there, what happens? The motor will always be chattering, and slightly goes to, then it will turn on, slightly goes below, it goes on shutting off, the motor will be going up, on and off. Whereas this will give you a natural characteristic which is required for turning on the motor without the chattering. So, this is a useful thing, it is not that it is a problematic to you. So, but it has a hysteresis, as against the comparative which I mentioned to you earlier, this does have hysteresis.
So we have the AquaGuard filter at home, where this happens. We have the AquaGuard filter at home. When it beyond a certain level only starts, below a certain level.
Yes. No, all water tank controllers have this circuit.